Hi everyone, thank you very much for joining us today. So we're actually back at the same location where we launched the AO testnet a year ago. And today we're excited to be able to start onboarding the first node operators. So today I'm going to take you through what is AO Core, the fundamental primitive at the base layer of AO, and how you can start running it on your own machines, as well as what the road ahead looks like and where we are right now. So, first thing to understand, of course, is that AO is a hyperparallel computer. It's a very different type of execution environment to traditional smart contracts. And that means that running nodes for this new environment is also very different. It's not quite the same as running an Ethereum validator or really any other chain out there. In this environment, you actually get to make a lot of decisions, and the users of the system engage in a market with the node operators for which devices that should be executed. But in order to understand that, we're going to first look at what AO does at a technical level, then how you can use it as a developer and a ecosystem participant, and then how you can get started running your own nodes, and then what we're going to be looking at in the road ahead from here. So first, I think in order to understand AO Core correctly, we really need to get back to the fundamentals of what blockchains are about. Maybe even it's best to think of it as, if you can put aside what you understand today as a typical blockchain, then you might be in a better spot to understand how this new system works. And then we'll work back up to what a decentralized network looks like in practice. So if we look from the, would you say, 30,000 or 100,000 foot view, what is the internet? Well, fundamentally, it's a distributed machine with many different actors that execute in parallel, and every connection between those machines requires trust. Now, we're used to working with encryption on our connections on the internet. When, for example, you want to access a bank or an exchange, there are different parties that are interacting. And sure, they'll be doing so using encrypted channels, so no one can eavesdrop on the connections. But the state transitions that are happening, so the bank says that someone has deposited their capital with the exchange, and then the exchange executes trades and then tells the users what happened. Each of those connections is dependent on trust in state transitions. Right? They're interactions that are happening inside this distributed network, and each actor is essentially, there's no other word for it than trusted to report accurately that those state transitions happen correctly. So each service is independent and tracks its own state, and there's no log of how the different states were arrived at. And this causes a fundamental problem that you can't interact with services on the internet that you don't already trust. And this is not just a hypothetical issue. This is actually a very real and extremely expensive issue. So even when you use a blockchain network, interestingly, you actually are largely trusting the RPC providers or the gateway providers in order to report to you accurately what's happening. Like every link in this chain is unvalidated by default on the internet. But you can add a blockchain network on top of it. But if you're still interacting through the old protocols and services, then there's no way that you're going to be able to get to certainty about what has actually happened. And there are quite a few instances where RPC providers or other sort of centralized services that sit on the edges of blockchain networks have caused problems for users. Some examples of those would be when DeFi networks have had their UIs hacked, and so users thought they were interacting with the network directly, but in fact they actually weren't. They were interacting with something else. But that's just one example of many. So in a traditional blockchain network layered on top of the internet, you have this sort of trusted zone, or rather trustless zone, where you don't need to have confidence in someone else's accurate representation of the state in order to get access to it or in order to see what is happening. Except those connections to the blockchain itself are still trusted, just like everything else on the internet in the default case. So it's like we've developed these islands, if you will, where there are small zones of trustless computation in a very, very wide network of trusted computation and communication. So the cost of this trust is not a trivial matter. You could look at this in many different ways. It doesn't just have to be in the provision of hardware. But if you do just look at hardware as one example instance of a wider problem, you see that there are these networks that can provide the provision of hardware for users. So let's look at storage, for example. We see that Arweave charges about 78 cents per terabyte month. And Backblaze, the cheapest centralized provider, charges $6. And AWS charges $23. And so why is it that Arweave miners are able to give up their storage space for such a lower cost than Amazon and Backblaze? Well, the answer is that for Arweave miners, they don't have direct access to the user base, and the users don't necessarily trust them in the same way that they trust Amazon. So Amazon is essentially trading on that trust. They've developed a brand and a reputation, and subsequently when enterprises want to go and buy cloud storage, they go to Amazon, not to Backblaze, even though Backblaze is a fourth of the cost. And what these decentralized physical infrastructure networks like Arweave allow us to do is to connect users at distance with minimized trust. So if you trust the Arweave network and it's fully transparent, you can audit it yourself and you can understand how the math works. It's a trustless sort of proof-based verification game that's happening about the storage of your data. Then you can, you can use it, you can deploy your files, your data to it, or your applications, web services, really. I mean, there's 15 billion pieces of information on Arweave at this point. So people are using it for many different things. And if you trust the network itself, then you don't need to trust the storage providers underneath. And those storage providers, while they have access to that storage, they couldn't just go and sell it to an enterprise customer because those enterprise customers don't yet have the trust in the provider, essentially. And so the cost of trust in these systems is extremely, extremely high. This isn't just hardware. You could also make the same comparisons for traditional finance services. For example, people go to Fidelity or the other large financial institutions for their ETFs rather than smaller ETF providers because they trust them. And if you look at the amounts of volumes going through those networks, or they're not quite networks, I guess, those services, you can see that that's an immense amount of combined cost that is being bared by the user base for something that actually is essentially algorithmic. There really should be no need for trust there. And so what AO does is it mimics the architecture of the internet, creating a sort of compute primitive that is parallel to the web, and works using the same actor model. So on the internet, you see many different services that are interacting, that bank and that exchange, that are sending messages between one another, and they're acting asynchronously. So each of those is running as its own independent service, essentially, only communicating when they need to. This stands in contrast to your traditional blockchain network, where essentially it's everybody's business what anyone's business is in the network. So for example, in Ethereum, if someone wants to trade on Uniswap, then the entire world stops while they do so. Everybody validates it. Everybody checks what happens, which, yes, does give you strong verification that the state transition was correct, but it's also immensely inefficient and will never reach the scale that we're attempting to with AO, building a decentralized supercomputer. So as well as this, AO offers a modular and flexible mechanism for minimizing the trust required between different parties inside the system. So we essentially provide, and this is really what AO Core is, a simple primitive for expressing there was this computation and this was the output, and linking that to an attestation from a particular party that is, would you say, it creates provable faults. So if there is a fault, you can see that it happened. And at the same time, there's also a mechanism that allows you to combine these proofs. So you can get many different people to attest, as many people as you want, but no more, in order to validate that the interaction happened correctly. And fundamentally, at its core, that's really what AO is. And everything on top of that is actually just utilizations and utilizations of that system, as well as sort of, would you say, modular combinatorial services that come out of the same base primitives. So AO core is simply blockchains expressed inside the HTTP layer of the internet. We boiled down the idea of a blockchain into its most fundamental elements and then expressed those in languages that are already well expressed and understood across a wide set of tooling. We really tried to build in the primitives of what blockchains can give us into the existing infrastructure, rather than going from the other direction, essentially, and saying, let's build an entirely new world and then have everyone try and adopt that. We built it into the stuff that already exists such that it can easily be adopted. And this is all made possible thanks to this new internet standard that was ratified last year, actually, funny enough, on almost exactly the same day as AO testnet went live. It's called HTTP message signatures. And essentially what it allows us to do is express a signature, as the name implies, inside HTTP requests and responses. And we thought this was really exciting when we first saw it, because we've always seen that Arweave data items have a relatively similar framework and form to HTTP headers and bodies, the responses that you get from web servers. And what this essentially allowed us to do was create a representation of data on Arweave as HTTP requests and responses directly, with no intervening formats, essentially. And have that be potentially, at the time we thought, and now we realize definitely, accessible with all the different tooling that already exists to support HTTP message signatures. And so that's deployment in essentially every programming language by default on day one. So when you get a signed response, or rather when you get a response full stop from an AO core node in your web browser, that last link in the chain that was previously unverified, unless you are running your own blockchain node locally, which essentially nobody does. It's not realistic to assume that they will. You get back this signed message, and you can verify that signature, and it essentially says, this person now attests to the fact that the resource, the HTTP, they call them resources, but we can think of them as pieces of data or services or representations of state that exists at this particular endpoint is this data. And this is the basic, we just say, it's one of the two fundamental building blocks of what make up AO core. And so now when we think about the networks that exist here, you have validation not just between the blockchain nodes, yes, you have that as well, but you also have validation to the edges, to Alice and Bob in this example. Their connection is just as verifiable as the connections between the nodes in the network itself. The other sort of building block that makes up AO core is hashpaths. So most messages on the internet that are returned, for example, let's think about that exchange telling the bank telling the exchange that the user has deposited their funds, and then the exchange telling the user in their web browser, this is your balance. These are linked interactions, if you will. One message has changed the state of another service, which has then created another message, which has gone to the user. When this happens, we can essentially create blockchain-style linkages between the interactions. So we can say message 1 occurred, and then message 2 happened on top of that state, and that got us to state 3, let's say. And so hashpaths are just a representation in the very, very simple sort of terms of a list of interactions, so a list of transactions that have occurred upon an initial state and a program. And if you're already familiar with the AO ecosystem, you'll know that basically the way that it works in practice is that, or the layer of processes, we create a log of inputs on top of a process. And we store these on Arweave. And we also have the program itself on Arweave, as well as the initial state. You add these things together, you can recompute the output. Well, AO Core takes that a level further and says, well, what if every message in the system, every attestation of a state, every message between the nodes even, so a user sends a message to a node, the node has to get the schedule, for example, for a process, and then gets a response and operates on that response, so it does the computation and then returns that to the user. Well, each of the messages that happen there essentially builds a tiny blockchain in AO Core. And this gives us, some really exciting properties. So one of which, of course, is that each of the responses that in this example the user gets, so say here the user has asked their bank to send funds to the exchange, and then they made a trade, and the trade affected these 5 people, just as an example. Well, each of the messages at the end of this process that goes to those 5 users will be affected by the hash path of the, will essentially contain the hash path that led to its creation. It's like a Merkle root, essentially, of all of the interactions that led to the output that you are seeing. And that's the output right to the browser, right to the user themselves. And that, again, is validatable using all of the basic primitive tools that already exist for the web infrastructure. So you can think of hash paths as a sort of atomic unit of verifiability. They tell you who said what, when they said it, and critically, why. So essentially, HTTP signed messages on their own, used in the way that AO Core does, would give you who said what and when they said it. But hash paths give us the why they said it. So basically, every node in the system, every AO Core compatible service is telling its users, I did X and Y and Z, and then I got to this output. And they're attesting, they're signing to say that that is true. So another interesting thing about hash paths is that they are pre-computable. This solves a fundamental problem where if you want to refer to a state in a network like AO that is hyper parallel, like there's no necessity of consensus even, and the consensus that's available or the sequencing that people use is flexible. They get to choose what type of sequencer they want. In order for that to work, you're going to end up with many different, how to best describe this? Many different paths, essentially. Like on a traditional blockchain, if you want to compute the path associated with a state transformation or a state in the system, let's say you're looking at Bitcoin and you want to know what happened when you applied X transaction on top of the chain at a certain point in time. Well, you have to actually compute the chain at that certain point in time in order to refer to the output. Hashpaths get around this problem and they allow us to say, okay, I want to know what happened when I applied A to B to C and what was the output. Well, the user can specify, they can pre-compute just by knowing the identifiers of the messages that are concerned, what the identifier of the state output would be. It's like a kind of hyperlink except across computation states. It's a really, different type of, it layers into the primitives of the web. I think hyperlink is a reasonable way of like summarizing it, I guess. But it's a new concept, a new idea. So one of the things this lets you do is compare the outputs at a particular hash path between different nodes in the system. Many people attesting to the state at a certain hash path, and then you can prove that faults have occurred. So if Alice, Bob, and Charlie all say that the state at hash path 1 is X, but Dennis says it's Y, well, now we know that there is a disagreement. And there can be resolution systems built on top of this to work out that resolution and resolve it towards something concrete, or rather a resolution of some kind. Two uses of the word resolution. Another interesting thing that this lets you do is combine state attestations. So one of the core features of HTTP signed messages is that you can basically sort of stack them. It's kind of like a multi-signature. And they originally intended this for use in situations where there's a cache or a proxy in between the user and the content that they're accessing. And those proxies can then sign the message as well when passing it downstream to the user. But we realized that in the context of AO, well, you can just use this to stack together all of those different attestations from Alice, Bob, and Charlie, and then perhaps Dennis is a separate one. And you can say, well, look, all of the votes are essentially in this direction, and Dennis disagrees. And you can have, ways of resolving faults using that mechanism. Another cool thing here is that the cryptographic algorithm choice, the signature algorithm used, is completely flexible. So in HTTP signed messages, the sort of base standard is called RFC 9421. Anyone that knows me personally knows that I must have said that word or that phrase 1,000 times in the last year. We've been pretty obsessed with it. It allows support for additional algorithms, not just RSA SHA-256-512, which is the base one that they use, although we do also support that. So you can use any key type on top of it, and the different implementations of HTTP signed messages all allow you to essentially mix and match them. So you could have a signature that is ECDSA or a signature that is RSA and stack them together and have it still be verifiable, which I think is unlike any existing multi-signature scheme in production. So it's pretty cool. And the final point about this that I think is, frankly, I don't think we even quite realize the full implications of what this means. But an interesting observation is that when you have, let's say, a system with 4 actors, so we have the bank, or perhaps it's a token process in AO. We have the exchanges, perhaps they are liquidity pools, and then user processes. Well, when you pass the hash path between these different actors in the system, the hash paths get combined. And so when you receive a message that is the result of, say, this 6th interaction on this user process here, if that interaction were to send you a message downstream, well, now you have a Merkle root, which is the source of proofs. You can create proofs against that Merkle root for the state of those other processes at those prior positions. And if you scale this out to the widest possible lens, you end up with this situation where the entire history of every interaction in every process or every service on the internet can be combined in essentially a single 256-bit Merkle root, which you can then prove the position of different interactions inside of. And this is really, really interesting, I think. It allows you to basically take one single root for the entire network and be able to prove faults against it, for example, and many, many other things. You can also change the hashpath algorithm because it's using RFC 9421 so that it will only accept a sort of valid new hashpath, only is acceptable if there are certain proofs about the underlying state transitions that went into it. So for example, you could use zero knowledge proofs if you wanted to, or TEE attestations. You say, I'm only going to include in this hash path TEE attested results, just for the sake of argument. Well, when you do this, you end up with, when someone gives you that root at the end, all of those different messages that happened will have attestations of state that you can prove against it. So you can say, okay, cool, I've got this one zero-knowledge proof at the end, or this one signature from this TEE node, and I know because of the way that that hashpath scheme was constructed, that when I go to position 6 on process 5040, then the output will have been precisely this other piece of data that I have. And that is proved because the hashpath wouldn't have been accepted by the downstream node if it did not come with that proof. And this, yeah, is very, very, very interesting, I think. And frankly, I expect that we'll be still working through realizing what that enables us to do, say 5-10 years from now. Just like with Arweave, we're still basically living in the downstream effects of what that simple primitive permanent information storage enabled us to do. So at scale, this gives you a single unified Merkle root for almost all of the computation in the network. The interesting thing is, because there's no enforced consensus, you don't get just one sort of root of the system. There are actually many at different points in time. But because these systems all interact, as they do, they're passing around and building the proofs together, which is very, very interesting. And also means that there's absolutely zero additional cost for this mechanism. It just happens, it's almost like a form of a state verification or validation, even arguably consensus about that, depending on the different hashpath algorithm that is used, that happens naturally as a byproduct of that distributed system that mirrors the operating model of the internet, just occurring, in the wild, if you will, without enforced additional transport complexity, right? When Alice sends a message to Bob on some, seemingly small-scale, unrelated transaction, maybe Alice is paying Bob to stream a video, perhaps, from Bob's server. Well, Alice paid Bob in a token, and that token, when Bob settles the payment, will carry with it the hashpath. And that hashpath will then go from that token to the liquidity pools that Bob traded it into. And then from that liquidity pool, then it will end up in largely all the rest pretty quickly. And so you get this sort of fuzzy head consensus, if you will, or at least verifiability of state inputs that progresses as people use the network with zero additional communication complexity and overhead. It's very, very interesting, I think. So AO Core is a primitive. It doesn't enforce any single virtual machine or security mechanisms other than those basic ones, the having an RFC 9421 compliant attestation mechanism, passing hash paths in the system. It doesn't enforce any specific rules for how you should use those. It's an architecture. And instead of enforcing one virtual machine, because there is no one virtual machine that will be perfect for all use cases, like it's unrealistic to think that that would work. It uses a system of what we call devices. And devices are essentially a form of sort of small state transition rules. They're kind of like components that you would typically find inside a blockchain system, but made into individual atomic units that can then be composed upon one another in order to have the net effect that you want. And this also means that they're reusable. So for example, AO processes, as we understand them today, which are built on top of AO Core, actually require the use of about, I would say, a minimum 6, but in practice more like a dozen or maybe 24 different devices, which can be remixed any way you want. So you could swap out the scheduler as one obvious example, but you can also swap out the execution engine and many, many other components like that. And from the systems that we've seen in the blockchain industry so far, there are, Cosmos and Polkadot have this relatively similar idea of, okay, we'll give you a blockchain kit, if you will, and then you can build your own blockchain with it and launch it in their ecosystems. Well, in that frame, AO Core is like, we won't just give you a kit, we'll give you pre-made Lego blocks that you can fit together in any way that is appropriate for your particular application. And we'll also give you a decentralized network, and that's what we're here today to get started building, of node operators who will run those different components for you. And that means that starting a new blockchain essentially goes from an operation that would require you to, frankly, like starting a power chain on Polkadot, it's like a multi-$100 million process. Well, AO Core makes it like you send a HTTP message to your friend, you go to a URL, any URL on a HyperBEAM node, and you've made a blockchain. And if you want to add a device, like a specific piece of functionality, a new consensus mechanism or rule perhaps, or a new state transition form, then 99% of the work is already done for you. You just add that one device, and then you make it available to the node operators, and they can choose if they want to run it or not. And this is where that market emerges from, for users and node operators. For, let's say, all of the node operators want to run this particular device, but the users aren't so excited about it, they want to run this other device. Well, the node operators that choose to run the second device will get more of the business. And so this creates a two-sided market, essentially, of supply and demand for the execution of devices. That is fundamentally what AO Core gives us. So then comes the question, well, how do you run it? Since the launch of AO Testnet just a year ago, we built out actually it was about 18 months to nearly 2 years ago, maybe, we started building the prototypes of scheduler units, messaging units, and compute units for the AO network. Those can now be thought of as essentially just specific types of device. And in fact, in AO Core, in Mainnet, they exist as devices, and they're pluggable. In fact, the process device is just an orchestration of all of those different components downstream, about 20 on average with a normal process that you start. And so rather than building in this direction that had 3 different node units that had to be managed independently, we realized this opportunity for the sort of X-unit platform, if you will. And that became what we call HyperBEAM. Hyper because it's hyper-parallel computer, and Beam because it runs on this virtual machine that was developed for Erlang, the programming language that essentially inspired the whole architecture of AO. And indeed, HyperBEAM runs on top of Erlang too. So it's a from-scratch re-implementation of all of the infrastructure that goes into running the AO network. And it modularizes, it turns into devices, each of those components that we now know, as well as opening up the playing field for many, many, many different varieties of devices to be made. I think X unit is kind of an appropriate way to think of it if you're already familiar with how AO works. So inside AO running on HyperBEAM, we see that there's many, many different stacks of devices that all work together to achieve what looks to the user like a single unified experience. So there are execution devices, there's payment devices, there's utilities that allow you to transform data in certain ways, and you don't have to rebuild those if you want to do something simple. You can just hook into the ones that already exist, as well as security devices, which allow you to give certain types of attestations to those hash paths and results that you're giving to end users. You can think of HyperBEAM as an operating system for running AO devices. It's a sort of open platform where you get to choose, almost as if it's like an app store, which devices you want to run on your HyperBEAM node, and then users can discover your node and give you business, essentially, proportionate to the different types of devices you're running, the cost that you set, and this is another thing. In a traditional blockchain network, there is a global price for usage because there is global consensus on every input and output. That isn't necessary, nor is it desirable in AO at all. What we do instead is we say, okay, well, you can set the prices. In fact, you use these pricing devices. You see them in a stack there, or rather payment devices, some of which are about pricing. They allow you to specify to the user, hey, you can run this computation using these devices on my machine. here's how my machine is spec'd, but I will charge you this amount. And then users can get different quotes between different providers. So what can you actually do with it in practice? Well, the first thing is every request is a blockchain transaction. And so that means that if you're an AO developer today, you can do something pretty cool, which is, you just specify in your AOS process that it should output something that is interpreted by web browsers as a web page. And so now your smart contract can deliver UIs to users based on real-time dynamically changing information. Here's an example where in order to make this, I just sent a message from AOS console with a content type text HTTP. I think it's application HTML or text HTML. Anyway, an appropriate content type as well as the data that I wanted to have rendered. And then I opened it in a browser and I just went directly to this URL. And when I did so, it renders the page. And it doesn't just render the page, but it also gives me a hash path and a signature on top of that page to tell me that it is an accurate, according to this node, it's attested, that is the correct data that results from that specific set of interactions on that process. This also has another effect, which is a utilization of the same, and I would call this like a byproduct. When we were trying to work out how to describe AO Core to people, and for what it's worth, we would love feedback on how you've understood this today, before we take it to a wider audience that's perhaps less technical. We saw that there were all of these very obvious things that it does, but they're really just byproducts of something much, much larger. And so hopefully you're sort of starting to grok that idea of what AO Core really is. But another thing that it gives us that is just a sort of random, it's a freebie that you get by designing the system in this way, is that smart contracts can output APIs. So just in the same way that we returned a HTTP message to the browser when you tried to access that web page, well, we can also give you back, for example, prices or the balances of users. And so your process can now maintain a HTTP accessible state representation, which users can then hit in their browsers. So say you want to, build Dexy is a great example. The liquidity pool tracking service that most people or many people use in the system, or PermaSwap. When you go to these pages, you see index of all the different prices of all the different assets on the different pools that are available. At the moment, in order to make that work, they use what's called dry runs. So they're essentially invoking that smart contract, that process on AO, and saying, what would happen if I ran balances or price? And then they're getting back the information. This requires a huge amount of computation. Instead, now they can just they can output it from their process, from the AOS WebAssembly container, just by sending a message, and they get back a sort of browsable resource, you could say, which can then reflect their API. So you could go to here, I had my HyperBEAM node on my local host. I've got stroke the process ID, stroke now, so for the latest state, the real-time latest computed state by that machine. And I go to price, and it will give me back the price, or I get the balances. It really doesn't matter. And another really interesting and exciting thing about this, which is more at the base of, or closer to the base of what AO Core is attempting to offer its users, is that these devices, they output states associated with hash paths in a fashion that can be cached. So you can build a CDN on top of a set of HyperBEAM nodes, and they will cache the results. And they can even potentially merge signatures together. So instead of hitting a compute unit directly, you have easily cacheable results from blockchain interactions that come with proofs or with verifiability and attestations right to the browser using all of the existing content distribution network infrastructure, which is extremely well developed. And this is just something you get from being built into the base layer transport protocols of the internet rather than being built on top of them. So yes, AO devs, no more dry runs. which is going to be a huge boon, I think, to the speed of which people get their responses from the network. So another thing you can do is trustworthy zero lock-in serverless functions at a fraction of the cost of AWS. Because AO Core doesn't enforce any kind of consensus rules, you can end up with offering a service which is essentially, you could call it consensus-free while maintaining the verifiability of a blockchain. So the node, if you were to construct the devices correctly, it wouldn't try and get a schedule or something like this in order to work out what order to apply operations in. It would just take the current hash path and the user says, I would like to execute X on top of it. And then it applies it, and then you've got hash path Y. And this allows you to do things like, well, I want to run one of those WebAssembly containers from those devices and get an output, which is exactly what you would do with something like AWS Lambda, the serverless function framework that they have. And you would get a proof back from it. So you can have some level of certainty, depending on the security mechanisms you required, that that is the correct answer. And it's available from a decentralized network where you didn't have to trust any one provider. And you can even take that hash path at the end and move it to a separate process, a separate node afterwards. It's mobile. And so you have zero lock-in. And to get a sense of just how big a deal this is, we could look at the size of the cloud computation, for lack of a better word, cloud physical infrastructure provision market today, which is hundreds and hundreds of billions of dollars that go into that in revenue every year. Well, now we can offer that with similar security guarantees to the levels, actually arguably exceeding those that you would get from AWS or a similar provider, by connecting people with hardware to spare that don't have that built-up trust and brand recognition that Amazon has with people that want to buy those services. And so we don't know what the prices will be for different services in AO yet, but there's reasonable, it's reasonable to believe that they will be far, far, far lower than they are today from the existing services. And that's just one really exciting thing that you can do with this system. Another is that you can heavily simplify deep-in networks. So I mentioned before that when you want to start up a new blockchain in AO, instead with perhaps a new cog, a new sort of, technically it's a state transition rule, but a way of transforming the program from one state to another, you only have to build one tiny, tiny component and then reuse all of the existing parts of the stack that you would like to, rather than starting from scratch, which just radically simplifies the process of getting a deep-in network off the ground. This is something we think, people will really be excited about, because we've seen this sort of rise in the prominence of deep-in for those reasons largely of, you call it like trust minimization arbitrage. People buy from Amazon because they trust Amazon, and you can essentially offer the same services with the same levels of trust, but now with far, far cheaper providers, you're sort of arbitraging the opportunity. This is a really, really exciting component, we think, that many people will get involved in. Arguably, you could almost see HyperBEAM as a deep-in operating system. AO processes is just one way of using it in order to achieve the effect of something that looks like smart contracts and has that same user experience, except much more powerful. But you could also use it for many, many other areas like storage, compute, you name it, anything you can plug into a computer. And those node operators can just choose, essentially like an app store, which devices they would like to run. So you have access to this open, decentralized network of willing providers of hardware to your new network on day one. And people are already playing with this. We told a few people in the ecosystem about HyperBEAM in the last few months as we've been building it, and some of them just started to build things on top, which was really exciting to see. So here is a draft pull request to the HyperBEAM repository, and you won't actually need to get your code into the HyperBEAM repository. The node is able to just download it from Arweave. But this one was sent there, and it allows web GPUs, so plugging GPUs into the HyperBEAM environment and making them available for people to execute on. That's just one cool example. It also makes your URL bar Turing complete for the, I was about to say nerds in the audience. I guess if you made it this far, you're probably a nerd. Sorry, guys. Me too. Yeah, each of the different components of the system are reusable just by calling upon their name, essentially. So here we can see the first example is we're at a certain hash path we call compute, which is a key or an endpoint provided by that device. And then we take the results from that. And then we say the WASM function that we want to run is factorial function, and the parameters are, can't quite read this little screen here, but 1 or 11. Yeah, so now you've suddenly turned the URL bar into a general purpose compute machine. But it can get much, much deeper than that. There's this sort of scripting style language that you can use to combine these URLs to achieve a task. So this second example we have, for example, is basically taking the output from a process and scheduling it. It's almost doing the job of a messaging unit in AO, but just by a URL that you can construct. And I think this really proves the point of quite how flexible this system is. And again, all of this is available in existing technologies. So here's a set of all of the programming environments and languages that already have support for HTTP signed messages. You can use it in essentially everything on day one, which is really, really exciting. Having seen the adoption process of Arweave, I remember vividly how difficult it was when someone came along, they wanted to integrate the system, and maybe they're using Rust, or maybe they're using Go, or C# we saw a little bit of. Well, you have to build out libraries for each of these things, and they have to be independently maintained. That isn't true with AO Core anymore, and because these data items, these messages that are produced, are a new form of bundling on top of Arweave, that also means you can upload data to Arweave using all of these different programming environments and mechanisms. Yeah, right out the box. It's pretty cool. So you came here to learn how to run nodes. Now you understand what this system is and how it's so different than the other machines. You're in a much better spot to understand what it means to run a node inside the network. So it's extremely modular. It's up to node operators to decide which services they run and how much they want to charge people for it. You can install new devices in the same way that you essentially provide new applications for an operating system of the traditional kind. Here's where things stand today. Each of those devices can be plugged in and swapped out, essentially upgraded independently. Again, just like an app store in a normal operating system. And that means that we can release them periodically and sort of update them over time. So we have three sort of internal and now I guess public representations of what of the maturity of different devices and protocols that we build for forward research. They are early access, so that's like they mostly work. You can think of it as alpha release. Preview, which is, okay, they're feature complete, but you shouldn't trust them yet necessarily. And then there's candidate releases. And those are, we don't think that this will need to change in the future. You can rely on its functionality to remain the same, unmodified, for an arbitrarily long period of time. And if updates are needed, they'll be very small. We call it sort of a Bitcoinization, essentially, that nothing that the Bitcoin community wouldn't accept becomes a modification to that particular protocol or device. Arweave is an example, and now AO Core of protocols with that level of robustness and resilience. So today, we're releasing HyperBEAM in preview mode. It's a beta, you can think of it as. You can run the node yourself, you can try it out, test it. It's, I would say, late stage of beta, the core implementation, running on top of AO Core, which we don't expect will change at all, really, from this point on. And there are many, many devices inside that are also in the green category of candidate releases. Those are very unlikely to change. There's also some that are in preview mode and others that are early access for really trying it out and playing with it. So those that know the AO ecosystem understand that the way that this got started is a year ago, right in this place, plus 2 days, actually minus 2 days, we started the testnet, and people started to use it for real valuable transactions pretty much straight away, which was exciting to see. Like the level of adoption and growth was extremely rapid, still is today. It's growing at an incredible rate. That means that there is this live network that people are depending on that can't just be abandoned. It's not like a normal test net where the devs are going to come along and reset it 5 times a day. Also, the data is stored on Arweave. And so the data is permanent. And because of the sort of holographic state or the projected state that AO uses in order to give you representations of what's happening inside smart contracts, if we turned off the nodes, all of the ones that we run and everyone else did the same, you could still, as a user, just boot up your own node and resolve a state upon it. And so this is interesting. It enables the opportunity for a live, smooth transition to mainnet in a way that wouldn't be possible if you had a full consensus system where there is, mainnet, which is inherently consensus incompatible with the testnet systems. That would be true for Arweave, it's true for Ethereum, and pretty much, I think, every other system out there. But we don't need to do things like that in the AO ecosystem, and we have this need not to because people are already using LegacyNet, we now call it, the network running on only the old versions of the node implementations. Yeah, we can instead smoothly, basically swap out in a live fashion parts of the underlying mechanism for HyperBEAM nodes, which you can now run yourself, while maintaining the existing LegacyNet, because all the data is shared, the consensus rules are shared, so there's no reason not to. So what we shipped on February 9th was this selection of devices. Basically, we created a payment relay, which allowed you to have a fast lane. And you could try this out on AOS, the AO operating system, in your terminal just by enabling mainnet mode. And people have been playing around with that for a couple of weeks. And this uses payment devices. It's speaking to existing LegacyNet node infrastructure, if you will. And that gives us this important ability to be able to have traffic that is, say, more valuable than other traffic. So LegacyNet's had many, many problems along the way, most of which are caused by people just running inordinate amounts of free computation. We wanted to offer that so that people could get started with the system. But now it's very clear, well, people need to be able to say, hey, I'm willing to pay to get my transaction done properly and to get the state of the system quickly. And this is exactly what payments from HyperBEAM enable us to do. And today, we're pretty excited to have a duplicated slide, sorry about that, announce the availability of Milestone 2 Preview. So this introduces many different devices that allow you to essentially run HyperBEAM resident computation. So using HyperBEAM scheduling units, using HyperBEAM pushing, that's the process of messaging, pushing messages around the system, orchestrating many different processes to act like one on behalf of the user, with embedded compute units. And this is exciting because you can do this in a TEE-enabled environment, which we'll get to in a moment, to provide trustworthy attestations of state to end users and charge them for it, and also have basically everything running in HyperBEAM, so that's AO core underneath, those HTTP signed messages being passed around. Yet you can still run LegacyNet, would you say, compliant or style execution on top of it. And so that's available today. You can go check it out on the GitHub. We're excited to see what people do with it. And next, we're going to be focusing on full LegacyNet compatibility. That's being able to run explicitly LegacyNet processes. And really the critical thing there is the scheduling units, speaking to those scheduling units from AO core in HyperBEAM so that you can get back a state of the wrapped R or the AO process and attest to it with that level of verifiability previously mentioned. And we think this is relatively close, but we're also now going to be building in public, so you can track the progress yourself. And we see here in this diagram the different levels of completeness and maturity we would need the different devices to be at. So that's next on the roadmap. And then the final component is having a green zone. And this is also something very exciting, we think should be coming relatively soon, is the ability to have not just verifiable computation from TEE-enabled nodes. So there's attestations you get back from those hash paths. They tell you with a high degree of certainty the correctness of the output, but also private computation, which, well, you name the things that could be useful for, but there are many of them. And the final step that we see on the near-term roadmap of what we at Forward Research would like to build, really at this point it's polishing it up. It exists in, I would say, kind of early access mode-ish, is a WASM execution environment native to HyperBEAM that uses this thing called AOT, that's ahead of time compilation, which will allow us to get near native speeds of execution inside AO processes. And so you stack all of this together, you'll have private computation with verifiable outputs at near native speeds, all running inside HyperBEAM. And as a node operator, if you get on board early and make sure that you can run those TEE-enabled computations, well, all of that traffic and usage will go to you in that open peer-to-peer marketplace I've described. But we're not the only people that are building devices inside the system. There's already 2 implementations of GPU sort of hardware additions as devices inside the supercomputer. Those are web GPU and also WASI-NN, both useful for slightly different things. One is more about rendering, the other is about executing LLM computation, but both using the same hardware underneath. And so if you can plug in your GPU, well, then you'll also be able to absorb the traffic and demand that is generated by those additional sort of components on top of AO Core. All right, so that's where we are. That's what we can do now in the system as it stands today. And yeah, we're super excited to help you guys get on board, get your nodes running, and basically build in the future. I mean, there's a ton of stuff to create. And we'd love to hear feedback on all the different components here, and also how we can better explain this to a non-technical audience. I think this audience is a really helpful starting point because you guys understand the technology underneath these systems. So when I describe it at its sort of fundamental level there, you can likely track along. But this is such a different way of thinking about blockchains and decentralized networks that communicating that to a wide non-technical audience and actually having it cut through the noise of blockchain space, I think it's going to be very difficult. So yeah, really appreciate you guys sticking around. And we're going to move to the Gather Town seating area, or the tables, where we can take some questions now. Thank you. See you guys.